Hi you guys, here's your notes on parallel circuits. So to begin with, I want to start by this is what a parallel circuit looks like. If you notice, it's different from what a series circuit looks like because there are multiple ways for current to flow. If you look, it could choose to go through here, it could choose to go through the 8 ohm, it could go through the 12 ohm. So it has actually 1, 2, 3 different ways it could go, which is one of the characteristics of a parallel circuit, that it has multiple paths for current to flow. Now, one of the things I want you to think about is if it has multiple paths, I want you to ask yourself, does it become easier or harder for current to flow in the circuit? So think about that for a second. If there's more paths, does it become easier or harder for charges to flow? Think of it like this. Think about it at the entrance to our school. If Schaumburg High School only had one door, would it be harder or easier for kids to go through versus having 3 doors? Hopefully you realize that it's 3 doors, even though most kids tend to only go to the one. It is easier for current to flow. That means because there's more paths, more charge can flow, or more current can flow. The more bulbs, or resistors, I should say, added to your circuit, cause an increase in current. Now, here's the other thing you guys need to think about. If you have an increase in current and your voltage stays the same for the battery and it's becoming easier, what does that mean for resistance? Well, remember, if voltage is the same, current and resistance have that inverse relationship. So as more resistors are added, then total resistance, or your REQ, must decrease. Now some of you might go, well, how in the world does that happen? Well, so there's a new rule for resistance. Yesterday in series, we just simply added them together because when you add more resistance in series, your total resistance increases. But in parallel, it does something goofy. So we're going to go back to like 3rd and 4th grade for a while, and we're going to do fractions. To find REQ, you use this. 1 over REQ equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. And I'll show you how to do that in a little bit, but that'll be the biggest thing that's very different for parallel circuits. Now, something else that is different is, okay, so that talks about resistance, but now let's go back and talk about current. We're going to have more current. The other thing that you should see is looking at knowing that these have different resistances and these are different paths. Well, that means current must be different in each of these locations. And as you think about what you saw last night as you did your homework, you should go, well, this current, this current, this current, how do they compare to the total? Well, they add up. Whatever this current is, plus this current, plus this current, must be the current coming out of the battery for the whole thing. So instead of it being the same everywhere, it is different. So current splits down each path depending on resistance in that path. Now obviously, again, just because of our Ohm's law that we've been talking about, the more resistance, like for instance this 24 ohm one up here, well, less current is going to go down here versus the 8 ohm. This is less resistance, much easier. Current's going to want to take the path of least resistance. So more current here, medium current here, least amount of current here. Current will still go, even though that's resistant, just like people are still going to take 90, even though it's back-to-back traffic and they say it's going to take an hour to get to Chicago. Somebody's always going to go that way. Okay, now to find current, then what we just said is we can say that I of the battery will equal I1 plus I2 plus I3, etc. Again, so a couple different rules here for resistance and for current, but just in terms of logically what's making sense about what's happening in our circuit, I hope these rules make sense to you. Now, the last thing we have to talk about is we have to talk about voltage. Okay, so thinking about voltage and going back up to our circuit again. So here we have 24 volts. Well, remember, for us labeling our circuit the other day, let me actually grab just a different color. In talking about it in terms of electric potential, we talked about this up here, having high electric potential. Lots of energy. Well, as it moves here, it hasn't lost any. So it still has high electric potential. Now, once current goes through here, well, then it's going to have 0 electric potential as it comes back to the battery. Now, if you notice, again, there's a whole bunch of current. So if I draw lines of current as 3 lines here, this is going to be my I. Some of this current will choose to go down this path. Some of it will keep going. In fact, you'll have 2 lines. Now, the amount of current that's going this direction hasn't gotten or hasn't met a resistor yet. So it still here has high electric potential because it hasn't used any. Now, some of this current will choose to go down this path, and by the time it gets here, it's going to have 0 electric potential. Notice here, it's just going to go right back to the battery. Okay? Now, so you lost a third of it here, a third of it here. I know those numbers aren't accurate, but it just the idea of it splitting. One of it's going to go this way. It still hasn't lost any energy, so it still has high EP here. And then it'll be 0 EP down here. Now, if you notice, all of these numbers are the same. They all end in 0. Notice your voltage here for every path is going to be the same. Okay, that's for a simple parallel. So let's go back down to our rules. And our voltage of the battery equals V1, which is equal to V2, which is equal to path V3, etc. Okay? Now, those are your rules for for what happens in parallel circuits. I'm going to post another video to show you a sample.